Hi, I am Yusuf Dalva, and today I will present our latest work StyleRes, transforming the residuals for real image editing with StyleGAN. Current GAN inversion methods can be divided into two categories. Low-rate inversion models offer high editability. However, as it can be seen, the identity of the output can change. On the other hand, high-rate GAN inversion models offer high fidelity, but the edits become low quality. You may notice the traces left in the background in the provided example. Let's start by reviewing GANs and their editing capabilities. StyleGAN can produce realistic looking images from style vectors. By applying some algorithms like PCA and SVM on the W space, we can get an editing direction, alpha. In this example, we add eyeglasses. To apply discovered edits to real images, we find the corresponding style code. Low-rate GAN inversion models train an encoder. However, this approach causes an information bottleneck, and many details are lost. At test time, we apply the known edits. High-rate GAN inversion methods train an additional skip connection between the encoder and the decoder. With this new setup, they can achieve high-quality reconstructions. However, at test time, the features are not changed correctly. We propose to incorporate editings into the training pipeline. To achieve correct editings, we apply transformations. As a result, we get editings that are faithful to the original image and with correct transformations. We incorporate all possible edits into the training pipeline using style interpolation. Let's say we have the input image 1. We randomly select a target and take a random step towards it. For this specific pair, smile, gender and eyeglasses edits can be simulated. We guide the network with the cycle constraint so that the edited image does not lose important details. Here is our network. Input image is fed to E0, which will extract the style codes. This network is kept fixed, similar to other high-rate GAN inversion models. Furthermore, we extract high-rate 64x64 features. These features are concatenated with low-rate features incoming from StyleGAN. Resulting tensor is fed to E1, whose job is to learn the missing details. Meanwhile, we randomly sample a vector and find the corresponding random target style, the source, and the target styles are mixed together using linear interpolation. This is how we obtain random edits during training. The mixed latent code produces a different generator feature. We introduce another encoder, E2, whose job is to transform incoming high-rate features according to the changed generator features. Notice that the gender of the input image is changed, as well as the hair length. That is why we randomly sampled a woman with long hair for this case. Also notice that the facial details are not lost after editing. We introduce two paths to train our network and one of them is selected with 50% chance. The first path is the reconstruction path. We try to reconstruct the input using pixel, perceptual and identity losses. We also apply adversarial loss on the output. Lastly, we apply feature regularizer because we don't want to change the generator too much. Note that this path is what other GAN inversion methods also use. Secondly, we introduce edit path, in which we utilize cycle consistency. We first apply a random edit, then we take back the edit and aim to reconstruct the input. If the facial details are lost when we apply the edit, reverting back would produce a person with different identity. This means the reconstruction losses increase. Therefore, the network has to learn to keep the facial and background details. We only apply perceptual and identity reconstruction losses. We also apply adversarial loss on the edited image. This encourages network to produce realistic looking editings. Lastly, we apply feature regularizer. It is quite important because there is a problem with cycle consistency. If the network simply passes all information from left to right, reconstruction and adversarial losses would be low. However, no editing would be achieved. Feature regularizer prevents this case because the network will be punished severely. With our model, we can obtain edits that are more faithful to the original image. In this example, we change the hairstyle and the text is still preserved. When we change the age, the microphone is correctly placed on the output. In this example, the top of the car is correctly constructed. Our model also handles the geometry better. Notice the background traces HFGI leaves when we perform pose editing. When we remove the smile, our model provides better shape. Lastly, our model creates correct textures when compared with the competitors. Notice the unrealistic teeth generated by Hyperstyle when we add smile. In this example, we try to reconstruct the image. Notice the unrealistic hair generated by the other approach. More examples and comparisons are given in the paper. Thank you for your attention.